And we are live. Hey there, Brendan.
Hey, Hugo, how's it going?
Fantastic. So great to see you. And sincerest apologies to everyone who's just joining. We went live on one link and we ended up having some challenges with YouTube. So as we get started, Brendan, if you wouldn't mind just introducing yourself while I email everyone or just send the link to sending the link to my colleagues to share with everyone so they can come over to this. That would be great if you wouldn't mind saying a few words about yourself and what you do.
Definitely, yeah. So my name is Brendan Collins. I'm part of a group called Makepath. We work on spatial data science challenges. We're particularly passionate about open source, and just wanted to start by thanking Coiled for inviting us to be here and being such a great member of the community. We're constantly benefiting from being downstream of Coiled and a lot of the projects that Coiled champions. So I'm really excited today to talk about what we're doing with Dask and Geospatial and seeing how we can use geospatial tools in scaling to larger problems and running on top of Dask to do that.
That's awesome, Brendan. And thank you so much. So having just put out some fires in real time to get us live, we're ready to rock and roll. As you've just introduced yourself, I just want to say a few more things about why we invited you here. We love the work that you do, especially like bringing up all the data visualization tools and geospatial data science from the PyData and SciPy stack, which of course are our communities. In my previous job, I did a lot of collaborations with Continuum and Anaconda, who you worked with as well. So all of these connections are really wonderful. I would love for people, we've got people joining now. My fantastic colleague, marketing manager, Christiana, has sent out the new link to this YouTube live stream. So we've got people joining. As you join, if you could introduce yourself, let us know where you're from, what you're up to, your interest in Dask and Coiled and all the geospatial data science with distributed compute that we're talking about. That would be fantastic. Definitely hit subscribe. For those interested in Coiled, we're building products that take the DevOps out of distributed data science so you can get back to your real job, essentially. So products for scalable compute, if you want to be working with larger data sets, larger models, complexity science, and don't want to have to do all the containerization and AWS foo and all of that yourself. One-click hosted deployments, which is super exciting for us to bring for you. We've got someone tuning in from Scotland, which is fantastic. I'm in Sydney, Australia. You're in Austin, Texas. Is that right?
I am based in Austin, Texas, but I'm actually in southern Mississippi right now.
Ah, okay. Fantastic.
And I'm visiting some family here.
Great. And thank you for tuning in from Scotland, Tyne. I hope I pronounced your name correctly, because it would be the wee hours of the morning there, presumably. It must be, right? Or what time is it for you, Brendan? So it's 5 p.m. for you?
Yeah, it's 4:15 here in Central Time, US.
Great. So let's just take a couple more minutes for people to roll on in and introduce themselves, because we're kind of getting started in a slightly, let's say, unorthodox manner. I'll just say you've worked on Datashader, correct?
Yeah, so I had the privilege of being part of the group that was doing Datashader right at the beginning. It really was the brainchild of Peter Wang and Jim Bednar and Jim Christ, and it was an amazing experience for me to be able to work with them and learn from them and be able to contribute to Datashader. Part of XArray-Spatial and the impetus for XArray-Spatial was that I was building a lot of geo tools within Datashader, and the geo tools became a little overwhelming, and it was time to break off into a separate library. But there's very tight integration between XArray-Spatial, which I'm going to talk a little bit about today, and its integration with Dask. But there's tight integration with Datashader also. And you may notice some of the maps that I have behind me, which were all created using Datashader and put together by Sarah Miller, who does just a really amazing design work for us. And so yeah, Datashader is a project that I'm very passionate about. I love Datashader and continue to work with it and contribute to today.
Fantastic. And those images are beautiful as well. Yeah, of course. And I think the first time you and I spoke, I mentioned that I was working in cell biology, biophysics, mathematical biology in Connecticut, in New Haven, Connecticut. And I went down, I just moved to New York City because Connecticut didn't agree with me. And I met the sales guy at Continuum. And he was like, I got this Python meetup happening. So I was like, great. I was in the big city. I was like, I want to get amongst it. I'd been using Jupyter notebooks and before that IPython notebooks as well. And so I went to this meetup and I was like, wow, a bunch of interesting people. Two people, there were three talks. I remember two of them were Brian Granger and Peter Wang. And I'd never heard, a couple of heavy hitters, right? I'd never heard Peter speak before or been introduced to him. And his firstly, his energy was off the hook, but he gave his Datashader talk, and this would have been like 2014 or maybe 2015, something like that. And that talk, those couple of talks really made me want to like learn more about the community. I went to SciPy conference in Austin that year, and really it was an incredible experience. And so Datashader was kind of part of the opening of my life to the community of the PyData stack. So that was really cool.
Yeah, I had my kind of intro to the PyData community happened in around 2007 when I was working at the Nature Conservancy, looking at reducing emissions from deforestation and forest degradation. That's the RED program. And I came across a problem that I couldn't solve through just brute force clicking in a GUI, and found Python as a potential solution. I downloaded this random PDF called A Guide to NumPy by some guy named Travis Oliphant. Walked over to Kinko's, printed that out. This is 2007, before the new version came out, before it was actually bound, and started to try to figure out what this NumPy thing was, and how I could use NumPy to summarize a lot of climate data that we were looking at for forest areas. And what a great experience that was in starting with Python, and just continued. I love the language, and it's been really great to see its popularity increase over the last decade.
Absolutely. And that, were you living in Austin at the time?
That was in Washington, D.C. I spent a good amount of time in Washington, D.C.
Yep.
And that is a real geospatial hub for the world. So many agencies there are pushing forward the geospatial tools, applying them to really interesting problems. And I continue to be in contact with the DC community, presenting to PyData DC last week. And so the geospatial side of Washington DC is really what attracted me to the area. And the Nature Conservancy was a dream of mine to work at. And so they're just a really great group, and I really appreciated the investment they put into me to learn Python and to help them push forward conservation goals.
Wow, that sounds like fascinating work.
It was really great, and particularly because I got to interact a lot with their Brazil team. I love language, and not only computer language, but also natural language. And that provided me a good opportunity to, get better at Portuguese and get, Spanish. And so I've always really liked systems thinking in general, from computer programming to natural language to music theory to gardening. All of these things are huge domains where you can lose yourself and go as deep as you want into them. And those are the topics that I really get excited about.
Awesome. So let's jump in. Speaking of Brazil, we've got someone watching from Brazil, someone from Santiago, Chile, someone from Madison, Wisconsin, India, Scotland. We've got people from all around. We don't have someone. There was one webinar I did once where someone said they were tuning in from Antarctica. I found that fascinating. The cost of the bandwidth must have been ridiculous, but they really wanted to get involved. If you're just joining, please introduce yourself in the chat. We're getting started a bit late due to some technical kung fu we had to perform. So if need be, and if Brendan has the time, we may go over past the hour slightly to cover all the great stuff we want to. But perhaps without further ado, we can jump in and you can tell us about the geo stuff and XArray and all the cool stuff you do at Makepath.
Great, thanks. Well, I'm going to start by sharing my screen here.
Great.
I'm going to hit the share screen button.
And anyone, feel free to ask questions in the chat as well. Anything that comes up, and I'll pass them on to Brendan.
Yeah, so Hugo, are you able to see the Makepath webpage right now?
Visualize what's hiding in your data.
Exactly.
Great.
So, so my name is Brendan Collins, just reintroducing myself. I'm the co-founder and principal at Makepath, along with Pablo Fuentes. And we focus on spatial data science, and specifically open source spatial data science. And a little bit more about my technical background. So not only is XArray-Spatial, just jump there, one of the projects that I'm involved in. We also mentioned the Datashader project, which I'm passionate about. But then we're also, 2021 for Makepath is the year of Bokeh. We're putting a lot of effort into improving Bokeh tools. And you may know Bokeh through the Dask diagnostic dashboard. So when you're using Dask and you're able to look at the execution of your graphs, the diagnostic dashboard was built using Bokeh. And now we're taking Bokeh and with the support of CZI and NVIDIA, adding publication quality reports for bioscientists. I'm also the creator of the King JSON Bible. If you're interested in doing NLP on top of the Bible, you may check out my King JSON Bible. But
that is a great name. Is it in JSON?
Yeah.
Form?
Yeah.
Awesome.
And so that's another webinar.
What are the keys and values?
Yeah. So it's yeah, book, chapter, verse.
Yeah.
And so the
wait, is it a nested JSON?
Yes.
Oh, even better.
Yeah. So so yeah, that's a fun one, and it was a fun afternoon of parsing the Bible. But yeah, so my true passion is geo, and that comes from a desire to better understand the world and questions that involve where. So XArray-Spatial is what I'm going to be presenting today. And to start off, I wanted to show XArray-Spatial.org. This is a website that you can go to start learning about this library and its value propositions. But you'll notice this subtitle here, raster-based spatial analysis in Python. And the key word here is raster. And I want to start just by defining a couple of terms that we use within the geo community. Between disciplines, there can be collisions in terms. We certainly know that the word vector can imply different things depending on the discipline you're speaking of. In the world of geo, we think of two different types of fundamental data, and these data types help us represent phenomena in the world. So we have vector and we have raster. So first, just to get vector out of the way, because we're going to be focusing on raster today, vectors are in the geo world are used to represent phenomena that are discrete. So we're thinking of points, lines, and polygons. And there's in just this image here, we can imagine maybe some of these, we're looking at Crater Lake National Park, but maybe these rivers are represented as lines. Some of the roads could also be lines. They may also be polygons that represent the area of the road. These are all discrete features. Cities can be represented as points. They can be represented as lines, as the boundary of the city, or polygons as maybe the urban area or the administrative area filled. And the key thing about vectors, right, is that they're represented using coordinates X, Y, and Z, and lists of coordinates to define our vectors. The other side is the raster side, which we use to represent continuous phenomena. When we think of rainfall, elevation, soil types are great for rasters. These are the types of phenomena that aren't comfortably represented using vectors. While there are ISO lines to be able to represent continuous phenomena, as we may know on a topo map, rasters are fundamentally grids that have a resolution and an origin and allow us to use all of our linear algebra that we love and the matrices on top of these data. And you can think of this dichotomy between vector and raster in other circumstances. So as an analogy here, Vector is Adobe Illustrator. Raster is Adobe Photoshop. So we see this difference between vector and raster represented in a lot of different areas. SVG is vector, PNG is raster. So when we say raster, we are talking about images, JPEGs, PNGs. Now those image formats are not the most common formats to do raster analysis in, but they certainly are regular grids, and they're composed of pixels, and we can, as opposed to thinking of a pixel as representing a color, we can use the pixel to represent data and do analysis on that data. So XArray-Spatial is a raster-based spatial analysis library for Python, completely open source, and uses Dask and Numba to be able to scale horizontally and scale vertically all of our analysis functions. So some of the tools that you're going to find inside of XArray-Spatial include 1D classification tools, focal analytics. So in the focal level of analysis, we're passing a filter or a kernel over the entire image, and we're summarizing and creating a new image based on maybe a neighborhood around a given pixel. So a smoothing filter or a mean filter would be a good example of a focal analysis.
I noticed we have some CuPy GPU stuff happening as well, which is pretty exciting, right?
Yeah, definitely. And that's a big area that we're looking at over the next quarter or two in making sure that all these tools are supported first with NumPy. And we implement first in just vanilla NumPy arrays. And these are XArray data arrays. And I can introduce a little bit more about what XArray is. But after we implement in NumPy, we then usually implement in Dask, then in CuPy, and then in Dask, CuPy. So if we wanted to support a cluster of CUDA GPUs, then we support that through Dask. And a lot of these are still being built out. And as I look at this, this is not the most up-to-date list. So why don't we go over to the GitHub page that has a better list here. So we can see
and I'll share this in the YouTube chat as well, so people can. Awesome. And this is XArray-Spatial.
Yes.
Right.
Yes. So this is github.com/XArray-Spatial, and sorry, Makepath.
Yep.
XArray-Spatial, and
don't forget Makepath.
Yes. Don't forget Makepath. Don't forget Makepath. So we can see inside of classification, we've added Dask support recently for a lot of the binning methods. These are classic binning methods that geo folks know by name. Some of these names, for instance, like natural breaks, may not be familiar to general data scientists, but we can think of natural breaks as 1D k-means for all the machine learning folks out there. But yeah, so we're looking to support these 4 cases for all of the analysis functions. And the library is a very flat, functional library. We are not introducing any new data structures here that the user needs to understand. We are building on top of solid tools like XArray, Dask, and Numba to give geo users the names that are intuitive to them, but using tools from the larger community. And it's this multidisciplinary aspect of XArray-Spatial that makes it powerful for geo folks. So as an example, within surface tools, so we can talk a little bit more about multispectral, but within surface tools, you may see a name like slope. And slope, folks in geography understand what slope means. Other people call it the first derivative. Other folks within NumPy may name it np.gradient. These are reflective of the disciplines of the folks that have implemented the tools. So what XArray-Spatial does is it looks at the larger PyData community, but builds tools specifically for the GIS analyst or the spatial data scientist, whichever name you like better. So we have So surface analysis tools, things like aspect and curvature. Aspect would be the direction of the slope in 0 to 360 of what direction a slope is facing. Curvature is the second derivative of slope, named for more aspects of the terrain. Illuminating with hill shade and a bunch of other ones, things like view shed, which is a line of sight analysis. We're going to be going through some example notebooks, but just to back up a little bit and look at the libraries that are involved in XArray-Spatial. So I'm going to make this a little larger for folks. See if we can get this a little bigger. So XArray-Spatial is benefits from being downstream of amazing tools. In aqua here, or this greenish color, we have the required dependencies for XArray-Spatial, which include Datashader, our rasterization pipeline, moving from vectors to rasters. XArray, which is provides label multidimensional arrays. We can think of when we're using NumPy, many times we have to index using integers. NumPy has a great slicing syntax, but it can be difficult to read other folks' code when they're referring to specific indexes using integers. And XArray provides labeled dimensions on top of NumPy arrays. So you can call a dimension soil or elevation, and you can refer to it by that name, and that makes the code much more readable. So XArray is a really great library and was the basis for Datashader. And being the basis for Datashader, that is a major reason why XArray was chosen for XArray-Spatial, and it's somewhat on the nose in the name of the library.
That's right. And I'll just mention I think I mentioned this to you previously, Brendan, but we did a live stream last year that people can check out with Deepak Cherian from NCAR, the National Center for Atmospheric Research, where he shows a lot of the stuff he works on in XArray and how he uses it there. So that's super cool and related to this. So.
That's awesome. I'm gonna have to check that one out. There are some other supporting optional dependencies here, including Rasterio for GeoTIFF and raster IO. CuPy, which is going to provide our GPU-enabled or CUDA-enabled multidimensional array. And then also, as we look at vectors, so these are our points, lines, and polygons, we want to be able to bring in vectors for analysis. And we do that using GeoPandas, which wraps the great Fiona library from Sean Gillies and Mapbox and Shapely, another Sean Gillies project, and ultimately Geos. And so we see at the bottom of this stack, we see both Geos and GDAL, which when you go far enough down the Geo stack, you're going to find one of these libraries most often. And that's a major difference with XArray-Spatial, because GDAL is not a dependency, explicit required dependency of XArray-Spatial. Everything within XArray-Spatial is implemented using Numba, and Numba is our interface to C. So the question that a lot of Python folks have when they're trying to scale up their analysis is, how do we deal with type checking within Python, and how do we make the tight loops in our code fast? If we're going to loop through 1 billion pixels, we need to be able to do that quickly, and we need to make sure that we're not doing something like type checking each pixel as we go. And that's where NumPy helps out with the homogeneous typed array container, and where Numba helps out, which is a NumPy basically a NumPy enabled JIT compiler. So it's a JIT compiler that understands NumPy arrays. So you can write your own more detailed functions, and we'll take a quick look at Numba in just a second. But I'm going to come over to the examples area.
I suppose I had one question, and we'll probably get to this about Dask. Is, people tell me they want to use Dask for this and that, and my first response is, have you optimized your pandas code, for example, right? Maybe do that before jumping to out of core or trying to distribute. And so I'm wondering when you would want to start using Dask for these types of things. But that could be later in the conversation as well. I just wanted to plant the seeds for a future tree to grow.
Oh, yeah, I love that question. That's a great question. So let's definitely address that. And what I'm going to be looking at here is in examples. So as you're browsing through this GitHub repository, go to examples and go to user guide. And everything that I'm going to be showing from here on out is available right here for download, and you can run it locally. In looking at how we use XArray-Spatial and some of the functions, I'm first opening up this Surface notebook. So in the Surface notebook, we're going to start by, we need to get some data going, and here we're using a generate terrain function to get a sample raster to do work on. This is just some Perlin noise so that we don't have to download an external data set to do analysis on this. And we're using the shade function from Datashader to actually render our raster and color map the raster. So the only part of this chain that XArray-Spatial addresses are the transforms on top of raster data. So here we're starting with a elevation color map. So we're starting to do color mapping on top of our elevation. And now we're illuminating using hill shade from a specific altitude and direction, the terrain, to have some light projected onto the terrain. So that's the hill shade function. But we start to see.
I just want to know, this is really like, you're getting a lot already out of some pretty high level code, right? And a few lines to do some pretty interesting, evocative visualizations.
Yeah, it's so the entire library is structured this way in that all inputs are XArray data arrays, and mostly all outputs are either pandas data frames or XArray data arrays. And so here in importing slope, where we're looking at where are the areas that might be at risk for avalanche. So in tying this to a real world issue. And here, once we've calculated the slope of our terrain, we have a new XArray data array where we can use all of our favorite NumPy tools and logical operators to then threshold that array to do our analysis. So all we had to do was use one function from XArray-Spatial, but then we're back into XArray or NumPy. And here I'm stacking the terrain with the hill shade and highlighting some areas of this mythical terrain that could have avalanches.
Great.
Not going to talk too much about curvature, but it is an interesting one.
And that's what you mentioned. That's the second derivative, the slope of the slope.
Yes, exactly.
Yep.
So when we're looking at the second derivative in GeoLand, we call that curvature. And that would allow us to look at basically, think of acceleration, right? The second derivative of the slope, but in 2 dimensions.
Great.
And all of these tools that we're looking at are 2D tools. So these are not 3D tools. We would love to have volumetric analysis and rendering here, but at the moment we do not. So some other surface tools that you might be interested in here would be the viewshed tool. And in this image, we have an observer, and we have a little mound here that was created using some Gaussian distributions from NumPy random module. And what viewshed will do is it will highlight all of the pixels that are within line of sight of our observer and tell us the direction that the observer would have to look to see that pixel. This can be used for a lot of different analyses, specifically service area analysis. So if you were looking at, say, cell phone towers, and you wanted to see what the line of sight service area was for that cell phone tower, this would be helpful. And we've built in a couple of features like how high is the observer and how far off the ground is the target that you want to see at that pixel, so that we can handle things like you're 6 feet tall and you want to see something that's 30 feet in the air. So in looking at viewshed on our mythical terrain, we can put our observer over on a southern slope, and then we can calculate our viewshed and see which of these areas this observer would be able to see. And that's highlighted here in Fuchsia. So that's a little bit about the Surface notebook, and also some references of where we found some of these algorithms and some additional reading.
Awesome. And I'll just say, anyone in the chat, if you have any questions, let us know. And if you've used any of this stuff or related tools, please let us know as well. That'll be really exciting to find out.
Yeah, and another really interesting area is proximity. And I linked Surface to like the avalanche example, but proximity has so many different uses, specifically for feature engineering. So if you're trying to find orthogonal dimensions for your machine learning models, adding in distance isn't a bad idea. There's 3 types of distance that you might be interested in. So we have, what we're doing is we're creating distance grids here. So we're starting with a pandas data frame, and we have X's and Y's and IDs for these areas. And we can see our points. We're using the Dyn spread function in Datashader so we can actually see these points because they'd be too small as single pixels. And what proximity will do is create an XArray data array of the distance to the nearest point at that pixel. So within proximity, if you call proximity directly, you can specify a distance metric. In this case, we're using Great Circle distance, but you can also use Euclidean or Manhattan distance to do this. And we get our distance grid back out. And this works with any XArray data array. So this is an array that represents a line, and we can calculate a distance map to that line. And we can threshold those distances also. And so here, this is somewhat of a raster buffer by filtering a proximity grid based on a distance. The other type, 2 other types, just quick, of proximity analysis that you might be interested in, allocation. So where we want the pixel value to be the ID of the nearest point. We don't care about necessarily the distance. We care about which point is the closest. And you can imagine how you could add this to your pandas data frames and then learn on these features. So this is allocation. So allocate all the area to one of the set of points. And the other one would be proximity direction, where what we care about is the bearing to the nearest point. Not necessarily which point it is or what the distance is, but we want to know the direction of the point. Imagine that you would be downwind of a fire, and the direction of the wind is particularly important in understanding what's going on with this fire. Proximity direction could be helpful for that. So that's a little bit about proximity. We're still working on proximity for Dask. And as we look at these tools, you want to be referring to the feature matrix on the README to know where we're at with that specific tool, but are always looking for contributions. One of the most important areas and useful areas are the zonal tools. So zonal tools allow you to summarize a value raster by a set of zones. And so using our mythical terrain again, we can imagine that we're planning a multi-day hike across our terrain. We have a couple of different line segments that represent the hike for that day, and they have IDs, and they're stored as a pandas data frame. We can then take the terrain, and we can take our zones and calculate some summary statistics for that zone based on the terrain. Here we get a pandas data frame out, excuse me. And for each one of our hike segments, we can have some summary stats about the mean, max, min, standard deviation, variance count of for that day. And one of a very powerful thing when it comes to zonal tools is writing your own custom zonal functions. So what we'll do is we'll pass in just the pixels for your zone to a function so that you can express any analysis or summary that you want to do on that zone as a function. And this means that this is the hook for adding any other library, third-party library, open source library, proprietary library that you want in the Python stack into this zonal analysis tool. So that's a little bit about zonal analysis here.
That's awesome. And maybe you could just tell us a bit more about, again, about use cases for that type of tool.
Yeah, definitely. So say you were trying to understand the distribution of agriculture in an area. Maybe you want to look at a specific county and you want to summarize the crops that are in that county. That is something where you would have one raster or an image that is a categorical image of crop types. And then you'd have one image that would represent the outline of your county. We put those two together, and then we look at only the pixels. So it's basically like a NumPy mask. So if you're familiar with NumPy masked arrays, we're masking our value raster by our zones, and then doing summary stats on those for the pixels in that zone.
Fantastic.
Comes up all the time, and there's two tools that
I imagine it can be useful in agriculture, in thinking about energy allocation, resources, in thinking about electoral polling. I mean, it seems like across the board, this type of zonal summary statistics and et cetera can be incredibly useful.
Yeah, and any place that like doesn't have explicit Dask support right now can still be used as part of a Dask bag. If you think of the Dask bag.map, you're able to still use these functions, but they might not be as nice of a spelling for you as the tools here that are already Dask enabled. So the Dask enabled tools will return to you a Dask graph that you can compute, while tools that may not have native Dask support right now, you could still use within Dask bag or map partitions, any of those hooks.
We actually had a live stream a while ago where someone, maybe me, was talking about Dask data frames and that being super important. And the Dask YouTube account commented in the chat, "I am more than data frames." And I thought that was super cool. And, you know, part of the message there, as you're alluding to, is that it's not just data frames or Dask arrays or Dask ML or this type of stuff. Dask is a general purpose framework and toolkit for distributed compute. And as you said, you know, sometimes if it isn't quite supported, you have to go in and do some of the stuff yourself. But it does allow you to do that.
Yes, and that, like, to me, I find myself using Dask all the time for multiprocessing. Anytime I have a multiprocessing problem, I'm looking at Dask, even if it's not a cluster-worthy problem. Because using just the vanilla multiprocessing module inside of Python, you miss out. There's so many edge cases that Dask handles well, including things like forwarding the standard out of a child process to the main process, dealing with zombie processes, and Dask, and specifically Dask bag. I'm a huge Dask bag fan. Really make multiprocessing easy in Python. So that's something I absolutely love about Dask.
Awesome. So just to let you know, we're about 40 minutes into the stream. We can go for another 20, maybe a bit more if you have the time, but yeah. Great,
cool. I want to make sure that we have time to talk about any questions that folks have. So I'm not going to cover all of these notebooks, but just a quick view of some of the classification tools which are generally supported with Dask. So these include, what we're doing is that we're summarizing a raster based on some binning method. And there is a general reclassify, but the idea here is that we've taken our elevation, and in this case, we've applied a quantile binning strategy. So in the quantile binning strategy, right, we're going to make sure that each bin has the same number of values in it. And in this case, we're doing 15 different bins, and we're ignoring a couple of values here. You can see this now summarized into areas that bin together based on their elevation. And there's other classification methods too, like the equal interval, where each bin is the same width. And then there's the natural breaks or Jenks reclassify, which is one-dimensional k-means. And in this case, we want to provide a sample and numbers of iterations that we're going to do to minimize. Basically, we're minimizing the standard deviation within any one bin is what natural breaks is doing. And then some regional tools. So if you're trying to pull out contiguous blocks within your image, then you can use regions. And so that would be a group by pixel connectivity that's another way that, and as you're thinking about this, you may not necessarily have a use case, but then remember that these tools are here to add features for machine learning. So you can take these tools and say, hey, what if we added in distance to fire station as another dimension in our model? This XArray-Spatial would help you do that. Some basic pathfinding. So here we're looking at pathfinding, raster-based pathfinding. The pathfinding tools are somewhat academic in that they were implemented just on NumPy, and we're actively working to create near optimal pathfinding for Dask. So we want to do distributed pathfinding on Dask. And here, so we have 4 and 8 pixel connectivity pathfinding. But then when we look at, say, the Austin, Texas street network, and we have an origin and destination, we can use XArray-Spatial to plot the course across the city and have those nice features like snapping your target and your destination to the network before starting. So we handle some of those edge cases for you there. I'm not going to go too deep into the code, but know that the code is pretty straightforward, and this slope.py file is a good place to start. So here we can see the CPU implementation for the slope function. We can see the GPU implementation for the slope function, which is benefiting from everything that the folks do in Numba. And we're just downstream of Numba consuming the great work that they're doing. And then also the CuPy cases and the Dask CuPy cases. And one of the areas of Dask, which is just huge for us at XArray-Spatial, is the map overlap function, where we can do analysis across a single partition and be able to do things like our focal analysis that may have edge effects if we didn't have this map overlap function. So really great stuff there. And then you can read the public signatures for our functions that include all of these backends, and then take this as a template to implement your own functions. I'm not going to talk too much about Mapshader, but I did want to say that we have a new open source project, which is taking Datashader and adding HTTP and OGC web services. So OGC is the Open Geospatial Consortium. They've published a lot of specifications for how geo should work on the web. And we're taking those specifications and implementing them using Datashader and Dask and Numba as the engine behind them. And you can learn more and see a little bit about the example config files that you can create to make geo-enabled web services. And we also put together a history of open source GIS infographic. You can find this, and we'll definitely pass these links over so that we can all share them. But
yeah, if you could share that link with me right now in the Zoom chat, I can then just share it in YouTube.
That'd be great. And
pass it along the platforms.
That'd be great. And I'm going to find the chat. I know that there's a chat here. And
if not, because you're sharing your screen, if you tell me the URL, I can also.
There you go. I think we got it in there.
Oh yeah, look at that. Fantastic.
So this infographic gives you a little tour of open source GIS projects, and they're not all Python specific, but they are all really great. And some of the ones to highlight, obviously NumPy and NetworkX were really big for geo. And also Shapely was an enormous contribution to being able to read shape files and features for open source. And then also some JavaScript libraries, so things like Leaflet and Cesium, which really help on the data viz side. If you'd like to learn more about Makepath, definitely visit the Makepath blog. We're always putting new content up there and highlighting some of the projects that we work on, and would also always be happy to talk about doing guest blog posts or having folks that are interested in spatial data science blog on our blog. And Hugo, so that's about my content, my structured content here, but also happy to take any questions and review anything that was unclear.
Awesome. I really appreciate that. We don't have any questions as of yet in the chat. So if anyone has any, please do feel free to ask. I'm really interested in this is all really exciting stuff. And how can people get involved if they're starting to think about this stuff? I mean, you mentioned some ways with Makepath, but what are other ways for people to get involved with Makepath and or the open source project?
Yeah, so starting in open source can be a little intimidating because one, folks have a lot of imposter syndrome, thinking, hey, I'm not good enough to go and contribute to an open source project. But there's nothing else that you need to do to get involved here than just to start. And you can start by going on to GitHub and setting up a GitHub account, looking at projects that interest you and being able to find the heads of those projects and the people that are involved and start plugging into the ecosystem. I think that documentation and testing is a really great place to start in open source. And I would certainly help champion and mentor any new developers or engineers that would like to come and contribute to XArray-Spatial.
Fantastic. I also have a general question around people who are interested and work in this type of spatial work. Okay, my question is, I presume there are a lot of people who don't necessarily haven't written Python code and that type of stuff, but are really interested in doing this. Are there, drag and drop, point and click GUI tools? And can we reach kind of the long tail of potential geospatial experts with non-coding tooling?
Yeah, that's so there's been a lot of really great graph programs out there that will allow you to create an analysis expressed as a graph. On the proprietary side, the one that jumps out right is a program called FME, which does a really great job on the geo side. But one thing that I had built as a proof of concept a long time ago was taking React.js and integrating it to create a Dask graph. So one of the things that I think would be really cool would be GUI tools for creating Dask graphs. That could then be where you have that representation in the browser, you serialize that to a cluster, and then execute that graph without having to write any Python code behind the scenes. I think that would be a really great thing. And so yeah, it is a hard. It's hard to understand, like, what's the best interface to interact with these analysis tools. Is it the command line? Is it a GUI? And I think that most folks want to start with a GUI, and QGIS in the geospatial world is the best one to start with. So when you start with QGIS, you are able to understand what tools are available and easily execute them. And as you want to go custom for a specific problem, you can then dive into some Python code and you can write some functions there. But you get a sense of the breadth of tools by using the GUI and seeing them listed out and seeing clearly what their inputs and outputs are.
Great, that's super helpful. So we have a question from Guy Maskell, which James Bednar's tuning in, and James has answered it, seems, but I'm interested in your thoughts as well. Guy has asked, so he's trying to get his head around a mental model of kind of the space here. XArray-Spatial depends on XArray, but implements GIS functionality that's independent of GDAL. Is that broadly correct?
Exactly correct, yes.
Great. Look at you, Guy. Fantastic. So I'm interested in thinking about some heuristics or rules of thumb for people who maybe want to start using XArray-Spatial with Number or Dask, or like how do you think about when to start using these?
Well, I guess with both Number and Dask, we're addressing scaling problems. So as you do work, you may find that it's appropriate to go to a Dask level. The first place that I see Dask is multiprocessing. So when I want to use more than one core of my machine, I'm looking at Dask to solve that for me. Then as my analysis scales up, I can move my exact analysis from my local machine over onto Coiled and then run on a cluster. And that's huge for us because we can prototype on our local machines and then we can deploy and run without having to set up all of the server infrastructure and PSSH into all the workers to install dependencies. And so that's one area. Also, one thing that I would say is that sometimes a problem that looks like it needs a cluster actually needs compression. And there's one of those compression libraries that I would highlight would be Blask. And if you look at Blask and what it's doing in terms of compressing data from disk onto into memory and keeping data compressed while it's in memory, you can turn what was a big data cluster problem into a simpler problem. So those are some things to highlight there. And what's great about XArray-Spatial, as you write, say, custom functions for the zonal statistics tools, you can express those as numba functions. So you can pass in JITted Python functions so that you can have performant code that's also custom. So you can write your own custom performant code. And numba and checking out the numba documentation is the place to start there.
Great. So we have another question from Howard Butler. Howard's asking, what opportunities are there to enhance base libraries like GOS and GDAL so they speak to this ecosystem better?
Yeah, well, Howard, thank you for the question, and I'm a big fan. So there's some opportunities that we're looking at to add GDAL as an optional dependency here as you install. Specifically, there's an issue to port GDAL warp. And yes, that issue has an exclamation point in it because it's very intimidating. So the reason why XArray-Spatial is where it is because of GDAL, because we had reference implementations to look at. If GDAL and GEOS weren't around, we wouldn't be anywhere right now, with XArray-Spatial. And so projections, definitely right now we're going to still go to GDAL. Raster IO is still going there. And then as we go, we look at new things. And there was somewhat, like when we started this, I had a very firm no GDAL rule as we started here to like get this going. But as we go, we see spots where it'd be really helpful to just be able to optionally install GDAL with XArray-Spatial. And so I think there's some good opportunities there. But GDAL is so far ahead in the breadth of tools than XArray-Spatial is. And if you look at the recent, let's say, vector tiles within GDAL and all the new features that are coming out with the projection strings, and GDAL is the tool to go to for open source raster analysis. XArray-Spatial is more of a niche raster tool that we're continuing to build out, but that scales well for Python.
Great. So if you wouldn't mind stopping sharing your screen, that means on YouTube they'll be able to see both of us. Although I have been told I do have a face and a voice for radio and podcasting. So those are all the questions we had. So we can wrap up in a minute. Something to wrap up with that I'm interested in is there's so much exciting stuff happening in this space. And I'm wondering, in terms of future music and the future of XArray-Spatial and all the work you're doing, what are just a couple of the things that excite you the most, that really pump you up?
So it's applying these tools to real world problems. So I care more about working backwards from a problem than we want to solve. A lot of the times I'm in the tools and I'm deep in the trenches of the tools, but finding real world problems where XArray-Spatial is just a little detail in the background, but that the solution is forward, and that's what really gets me excited is seeing these two tools used for solving real world challenges, and specifically the use within the Pan-Geo community. So supporting Pan-Geo, which is a consortium of private and academics that focus on climate change and building tools to understand the climate. So out of everything, I would say if we can continue to build these tools to support the Pan-Geo community, that's what kind of my number one is.
That's awesome. And I will say not next month, but I think the month after, we're actually having Shell Genterman, who's an oceanographer, who's very deeply involved with Pan-Geo on for one of our live streams. Yeah, and we chat with Ryan Abernathy a lot and work with him as well. So that's super exciting stuff. I had another question, which is slightly tangential around. I'm just still like blown away by the image behind you there. I'm wondering about, because it's beautiful, right? But it's also information rich. And I'm wondering if there's some tension or trade-off between building visualizations that are attractive, yet you want to convey a lot of information there as well.
Yeah, it's I mean, I got to say that there is an element here of storytelling, right? Of being able to communicate insights to people. And there's a lot of great visualization you can do, but if it's not supporting a story, then it's somewhat useless. And I think a lot of, the classic hero's journey of like 5 acts in storytelling and being able to take a concept and communicate it. And some folks are very distracted by colors. I've worked with academics in the past that don't want like anti-aliasing in the text because they, it's not raw enough, or it takes away from the data in some sort. But I think that keeping the user in mind, keeping the problem in mind, and working backwards to the visualization that makes the most sense to communicate the insight is the way to get around a lot of those issues. And I think where there are problems, it's because they've started from like, no, I want to make a hive plot, or no, I want to, this has to be Datashader, and instead of starting with the problem and working backwards.
Yeah, that makes perfect sense. So to wrap up, let's just tell people how they can get involved again if they want. You mentioned that the GitHub repository that we shared is a great place to get started. They can definitely ask any questions of you there and that type of stuff as well.
Definitely. And I just want to stress that this is for all technical levels. So even if you're just getting into Python and you want to learn a little bit and you want to start contributing, there's a place for you here. And checking out the Makepath blog and seeing some of the projects that we're working on, you're always welcome to reach out to me on GitHub. That's probably the best place to reach out to me. I don't actually use too much social media or Twitter or anything, but I am on GitHub. And so there's just opportunities for everyone to come in here and understand what's going on and make really valuable contributions.
Fantastic. Well, that's it, everyone. Oh, no, we've got one more question that just rolled on in from Guillermo. Yeah, this is a great question. Where can we find interesting open data sets to use with XArray-Spatial?
Yeah, so I mean, I think of the USGS kind of Earth Explorer and some of what's available through public entities. Depending on the country that you're in, there different public entities may have data. For instance, I'm very interested in Brazil. I love looking at Brazil data. IBGE is the Brazil census. So I go on to the Brazilian census site and I download shape files or I download geotiffs. There's also really great public data sets out there from universities. So Stanford University has a really great geo program. And then also, just to get started, there are sample data sets inside of GeoPandas. So you just download GeoPandas or you download Bokeh, there's a bunch of sample data sets. Datashader has a fetch data command that will download all the sample data for Datashader. And you can start playing with the tools with those data and then find data that you're more interested in and drop it in and have a template to start from.
Great. That's awesome. So, Brendan, thank you so much for such a clarifying, informative, and fun live stream.
Oh, thank you, Hugo, and thank you to everyone at Coiled. Just really, really privileged to be with you.
Awesome. Appreciate it. All right. Thanks, everyone.